Hello and welcome to today's XP Solutions webinar. My name is Gavin Fields and I am the Senior Water Resources here at XP Solutions. XP Solutions webinars return today in 2016 with the topic Urban Drainage Design. Hopefully today's webinar will be useful whether you are new to designing urban drainage systems or you're a seasoned expert looking to learn a few tips and a couple of tricks out of today's session. Rather than bore you with too many slides on theory today, I'm going to try and keep the slideshow component as brief as I can and have a bit more of a hands-on session at the back end of today. And all things being equal, I'll get a model up from scratch all the way through to hopefully having some results. So we'll see how we go. Again, big focus on today's webinar is to have a bit more of a practical presentation, and I want to try and go into some of the more in-depth use of some features in the software and how they can be best used to design stormwater networks. Okay, so just quickly about XP Solutions for those of you who are potentially new to us. Obviously, we're a software company and we provide tools for wastewater, stormwater and flood solutions, as well as a number of other activities including asset management and street sign design as well. Particularly in the US markets, but for the Asia Pacific market, which is a bit of a focus for today's webinar, definitely the stormwater and flooding is a big part of our demand by our client and user base. Very proud of our interface and all these things that we can do with our software. So just an overview. Today's session is I've got a few components to go through, have an introduction, some objectives of urban drainage, and go through the guidelines and requirements of why we do this, and then we'll get into the practical application, some demo stuff with Q&A at the end. So, urban drainage. Certainly in my perspective, and I'm sure many of you will agree with this comment, that urban drainage is by far and away the most common application for stormwater design. That's what most of us get paid for, or the reason we do what we do on a day-to-day basis. And by no means is urban drainage new. And this little photo is a happy snap I took last year whilst I was in China. And this urban development area is about 700 or 800 years old, and a very, very complicated urban drainage network. Very, very clever. And they didn't even have XP Solutions products to work all that out. So it's good to see that urban drainage is very important. It's been recognised throughout the history that we do need to deal with stormwater. And so what are the objectives of urban drainage? Well, primarily, we want to design stormwater conveyance and then more recently water quality improvement structures from allotment scale developments through to defined overland flow paths or water courses. So that's quite a broad statement, but it does cover what this particular webinar is all about. And we do that by starting to assess our local catchments. And our local catchment assessment must include, of course, hydrology, local hydraulics, and, if as required in your region, water quality. And these three aspects of urban stormwater drainage really underpin integrated water management and the procedures that certainly myself and the other team members here at XP Solutions really want to ensure the stormwater industry at large can tackle in an efficient way. And further, we want to ensure that our urban catchments cause minimal nuisance. And nuisance is a very interesting word. What does that mean? Nuisance is typically revolves around impact on other properties with respect to peak discharge. And some of you may have had to deal with the term non-worsening to avoid nuisance. And that's where we look at trying to assess our hydrology for existing cases prior to urban development, see what the difference is, and then introduce engineering solutions that offset the potential for nuisance. We want to ensure that our urban drainage systems are safe. And the particular photo that I've got here is actually an instance of where I don't think it is that safe, where we've got a footpath solution with an elevated field pit right behind a pedestrian footpath. If you were to fall off that footpath and land on that grate, I don't think you'd be too happy about yourself. But we really try to avoid situations that create trip hazards, safety issues, and this is in a dry situation, let alone when we put water into play. You wouldn't want to be swept in there due to flood water, and we'll talk a bit more about safety later on. We want to try and reduce impacts on built and natural environment. We want to avoid scour, avoid erosion, and of course avoid damage to property, as all of our insurers want us to do. And protect and enhance the downstream environments when it comes to water quality. And this little photo here on the right hand side shows, it might be a bit hard to see, but hopefully you can see the turbid colour of the inflow to this particular wetland. And this wetland is really in the middle of construction of the urban catchment upstream, and it's during those construction phases, of course, that water quality devices probably suffer the most, but it's when they have the greatest potential to protect those downstream environments. And good design of sedimentation processes, stilling basins, and those other functions, gross pollutant traps, can really help improve the performance of natural systems like wetlands. Getting the size of those right is always important, which leads to cost. One of the typical mantras of a civil engineer is that they need to undertake their engineering design in a cost-effective manner, in a way that the community accepts those costs for the greater good. So guidelines and requirements. Guidelines and requirements are obviously derived around problems. We try and assess issues, and here's a photo showing a blocked inlet to a drainage system. And these sort of issues trigger our guidelines. Hopefully your inlets get blocked before our pipe systems. In this situation here, asset management guidelines come around this aspect, and this triple set of box culverts has certainly seen better days, with the reinforcing all being fully exposed through decay of the concrete, erosion of the surrounding terrain, and that could eventually lead to a significant issue with respect to that pavement that the culvert in itself is actually trying to protect. We then get situations like this, and I'm sure if you've seen any of my webinars in the past, you may have seen some of this, or photos of this particular area. This is where outside my office, and the vehicle that is at 30 degrees to the footpath in the road there has floated to that position. If we go downstairs in that photo, we want to avoid situations like this in our urban environments where vehicles feel that they deem it necessary to drive through inundated roads, because that not only creates issues to the vehicles themselves, but can create issues to pedestrians and people around them. And again, you can see those two vehicles in the background floating around like toys. So in this sort of environment, it could be that your urban drainage design is all about mitigation. How can we avoid this kind of inundation in this particular location or any other location around the world? And it's important. Today's topic's not just about Australian guidelines, but there are lots and lots of guidelines, textbooks, manuals, and some popular ones that I will talk a little bit towards today is obviously the Queensland Urban Drainage Manual, which is a very, very good document, and I don't care where you're from in the world. I think getting your hands on a copy of that document, which is freely available on the GIS website, it would be worthwhile. Australian Rainfall Runoff 2016, not quite finished with Chapter 9 being the urban chapter, but that will hopefully be on our doorstep in the next few weeks or months. Getting further abroad, another really good document that probably the Australians in the audience might not be aware of would be the Urban Stormwater Management Manual for Malaysia by the Department of Irrigation and Drainage. And it at times actually does refer to the Queensland Urban Drainage Manual, but it in itself is a very good document. And for our brethren across the Tasman in New Zealand, the Auckland City Council Code of Practice for Land Development and Subdivisions is another very, very good reference document. It talks about urban environments. And so what are the requirements of these sort of guidelines? And this is a little table on the left-hand side here from the Queensland Urban Drainage Manual, or QDM as I'll probably refer to it for the rest of today's talk. But we have these parameters on the left-hand column, and I'll stick just to that column for speed today. But we've got to look at things like drainage efficiency. Why are we building whatever it is we're going to build and address the desired outcomes? Obviously, flood control, we want to avoid flooding like we saw in those photos a moment ago, which requires an assessment of runoff volumes, which leads us to the image on the right-hand side with a typical hydrograph, where we look not only at just the peak surface runoff, but the volumes underneath that curve and inherently the velocities that come with that. And so flow velocity and discharge with depth are the foundation of your hazard analysis. Water quality is then a subsequent function of that hydrograph on the right-hand side, particularly if sedimentation is something that you're worried about. Aesthetics. I'm an engineer and I like rectangles, and so sometimes landscape architects have a very important role to play to bend my hand to ensure that the work that we produce is attractive and meets the needs, the collective needs of the community, rather than being specifically fit for purpose and rigid. But again, I'm also worried about the cost of both the aesthetic component and the functional aspects. These are a couple of two really important slides, I think, that all urban drainage design engineers should be focused on, and probably are already. But that comes back to safety. And these are two really useful diagrams that have come from Australian Rainfall Runoff and some reference texts therein. But this talks about the speeds and controls with which humans are subject to falling over or being swept away in floodwater event, and also the impact on vehicles. And of course, the photos I showed before showed a couple of vehicles floating, as per the bottom example on the bottom right-hand side. But it doesn't really take a lot of water, nor does it take a lot of speed of that water to create a significant impact. And that Chapter 9 in Australian Rainfall Runoff, Section 2, has some very good guidance on what the maximum velocities versus the minimum depths. And so if you have a 3 metre per second flow, the maximum depth should only be 0.1 of a metre on a road. And so that DV combination becomes very important to protect vehicles and humans. So have a look at that reference guideline later to track some of those more detailed numbers down. So getting close to the end of my slides, practical applications. Obviously, we want to try and generate this kind of output, but we do that through integrating the design of these systems, hopefully, using full hydrograph methods, and certainly that'll be a requirement in Australia pretty well from now on, using Australian Rainfall and Runoff 2016 to assess again volume, peak discharge and velocities. So that's the end of my slides, I'm pretty sure. It's time to try and crack over to our software and some other tools to go through what I suppose we talked about in our market. And one of the things that we've been asked to do by a number of clients was to talk about how data can get into our software. And just as an example, and it's not a recommendation here, it's just an example, but I've actually got a project here that is going to come from 12D. And 12D is just an example. You could use Civil 3D or our own Site 3D. We have our own 3D Earthworks package, but this is just an example. We do link pretty well with 12D, so it makes my life a bit easier. But if you've already got a project that has a layout, a civil designer has already gone through and done some preliminary gradings, and you, the stormwater engineer or designer, is being asked to finalise or confirm both the minor and major drainage for this particular site. Sometimes the tools in these simpler programs may or may not be good enough, and that's where hopefully XP Solutions can step in and help you out. So in this particular project, everything's been relatively well set up with some basic rational method style calculations to size some pipework. And if I zoom in, I don't want to pan around too much on this, just with the speed of today's session, but We do have a pipe network under the road system, as we can see with the contours there. And if I go into the design menu under drainage sewer to the network editor, I can pick said drainage network. Let's try and grab one. And if the model has been set up well and the details are all inside the network editor, we can actually export directly to XP Swim or XP Storm by going to the Import Export button. Under the Input Output Format, XP Swim sits in the middle, and I'm going to create a file, a brand new file, because I've done this on a trial to prove that I could do what we're talking about today in time frames. Call this XP from 12D for demo. The file created will be an XPX file. If I hit the Run option at the bottom, it will spit out a text file that, with one extra step, we can bring directly into Swim. So the drainage model has been exported successfully. So I can go back to the network editor and hit Finish. And for all intents and purposes, in this brief demo, I'm finished with 12D. I can do a very similar process again with any of those other programs like Civil 3D. The current version of XP Swim and XP Storm is the 2016 release. We're not far away from having an update for that. We have had a couple of minor items that needed to be improved, and hopefully we'll have our 0.1 release. 2016.1 will be in the first or second week of February. I'm going to create a blank file from a template just to try and prove again how easy we can do this stuff from scratch. And I'm going to call this, whoops, if I can type, Urban Demo 2. Oops. And as a template file, one of the two files that do come with the software installation these days is the master metric or the master US template. So if you are in feet and inches, then by all means you can use US units, but to my knowledge is only I think Burma and America that continue to use those units. So let's press on with the master metric for today. And I effectively have a blank model. Just to simplify things down to start with, I'm going to minimize my 2D model and reporting, but I'm going to work in my 1D network space and create this model as quickly as I can to try and produce some results in the allotted time for today. I'm going to start by bringing in that network that we've just exported from 12D. And so under my File menu, via the Import Export Data option, I can import an XPX file. I'll just remember there was that one extra step that I needed to do. And from 12D at the moment, if I go to where that file was exported, in fact, I'm just going to copy this into my working folder. This XP from 12D demo, the file format is actually in a specific encoding type. And at the moment, 12D is exporting all of their text files as a Unicode, or this UCS Little Indian is one of the encoding points. What I need to do is just open it up in a Notepad editor, a little bit more serious than Notepad by Windows, but this particular example, Notepad++, does actually come with your XP installation, so it's a freely available tool. And all I need to do is just encode that in ANSI ANSI and hit save, and I can close that down, then import it into Swim. So I'm just going to select the file. It always takes us back to the last folder we were in, which was the templates directory. And I have a folder here, Urban Drainage, with the XP model, and I want to grab that XP from 12D demo. Hit import. It's a warning saying that if there had been any data, it would overwrite it, and it's now bringing in the file. Get a warning about some names, but I'm not too fussed about those for the moment. And if I zoom to the extent of my network, there is the data that's been directly imported from 12D. Simple as that. Just to tidy that up, I'm going to turn off some labels, just so I can see things a bit better. In fact, I will turn off the node labels as well, and trim that down. The next steps of this particular project, I'm going to bring in the terrain. I'll do the terrain for a couple of reasons. One is to give me the ability to assess overland flow in either 1D or in 2D. And I'll show you both in today's quick demo. So under the DTM layer, under topography, I can load a DTM. Today I'm coming from 12D, so one of the file formats that we can bring in is our tin.0. We can also bring in 12DA files. We can bring in land XML from Civil 3D, XYZ, data from GIS packages. I think we're pretty flexible on the terrain. I've already tested this before, but I'm going to go back to the raw 12D data just to show how that can be done. And if I find that design tin surface came from 12D directly, it's the tin.0 format, I can hit open. It says it'll do a quick conversion and it will bring that terrain file into our software. But as you can see, just the design component of this project might not quite be enough. I would need another component. So a good feature of XP's products is that we can actually handle multiple surfaces at once. So I'm going to load in a second terrain file from 12D, and in this instance it will be the existing. I beg your pardon, I want the entire site. And so now I actually have two surfaces over the top of each other inside the interface. And I can flick those on or off for display purposes, but they will hold there forever. I'm just going to change their properties to turn off the fill color, and I'm just going to contour them with some 1 meter and 0.5 meter contours for each of the two surfaces, and that will simplify our screen down. And there we are. Maybe some 0.25s would have been better, but half meter contours, everyone gets the idea. Now, I might even turn those off just for clarity in the short term. The next thing that I want to do is actually look at my hydrology. And we have 3 modes to XP Swim, 2 in XP Storm. But I'm going to go to the runoff mode next and start to deal with catchment hydrology. 12D has been kind and sent me some of the information from the Drainage Network Editor, which is lovely. And I'm going to play around with that now. So I'm randomly going to select this node here. And 12D has provided me with a catchment area of 0.084 of a hectare in this example, with a fraction impervious of 90%. This project was actually a relatively high density project, so 90% was pretty well used across the board, with a slope of what, by looking at it, I'm going to guess is 2.5% slope. At present though, XP Swim sees this as meters per meter, in which case this is a very steep slope. This is 250% slope. So I need to put in a parameter to adjust that, which I'll do shortly. And I'm also going to change my hydrology method to use Lorenzon's method inside the software, where I'll need to do a land use split to extract out the 90% impervious to a separate subcatchment, with the balance 10% impervious as a pervious entity. And we'll do that quickly using Excel. But just as an example, I'm going to go into this particular node and switch myself to Lorenzon's method for the hydrology. And we can see here that I need to get some rainfall information and also some infiltration. So I'm just going to start with infiltration. And I'm going to add 2 infiltration types, one for the pervious and one for the impervious. So I'm going to have an initial loss of 0 and a continuing loss of 2.5 millimeters. Press add, then edit. To get to initial continuing losses, it's a uniform loss, 2.5 millimeters there. Change some Manning's values just to better reflect my catchment, and otherwise I'm okay there. And I'm then going to duplicate this particular record, but rename it to be the impervious record with 0 initial and 0 continuing losses. And I will select that I equals 0, C equals 2.5 next. I'm going to hit OK. I'm going to leave this dialog box because I'm going to do all the hard work in what I feel is a faster mechanism, which is our table editor. But the next thing I need to import to my software is some rainfall. And I strongly recommend people to have some good templates for rainfall data. Please get in contact with us afterwards if you want to discuss more about that. Rainfall data is going to change with, here in Australia at the very least, for Australian Rainfall Runoff 2016. But if you are overseas, then again, using similar functions, you'll be able to create your own rainfall data. Back to my model, and I've got a sample file for Brisbane rainfall data, a place called Eagle Farm, as today's example, and I'm going to import that data in. So, getting through my list, I just want to change that configuration parameter to get rid of the slope issue, and the configuration parameter is cat slope equals a percentage sign. And if I hit add there, that's a very, very powerful parameter. And now that 250% slope is now actually 2.5% slope. So very important. Okay, so the next element we want to do is get ourselves into editing those areas to be able to run our hydrology. To do that, I'm going to go into our function called XP tables, and it's this spreadsheet looking icon at the top, or F2 on your keyboard. And I'm going to go to all objects in the model with this little drop down on the top right. It's what I'm going to come back to a couple of times. But I'm going to sort the catchment flag. This information did come from 12D. And I'm going to highlight the nodes in the model, which 12D has said are either head wall outlets or junction manholes. So they don't actually have a catchment attributed to them. And I'm going to show these in the network by pressing this target looking icon at the top here in XP tables. And you'll see that all of these nodes, which were squares, are already off, which is useful for me. And so I'm happy that they're not part of my calculations. So that was a bit of a check. Back to XP tables. The next thing that I want to do is review the area column, because sometimes modelers might make mistakes, and so I've actually got a file that's got a couple of little mistakes in it, and it's useful to see those. And as part of this, you'll see here that these nodes here have 0 hectares attributed to them. Whether that's right or wrong, we'd need to go back and talk to the original designer. But I'm going to go into here, and from that selection, I can actually disable these from our calculations by pressing a minus button. I haven't deleted them, but I've fundamentally turned them off. And I'm going to close XP tables at that point to allow it to refresh, and I'll hit save, of course. Hopefully, probably only the second last time I'll need to go into XP tables, but what I'm going to do now is, now that I've disabled all of those components, I'm going to sort, again, Z to A, and this time I'm going to highlight the nodes that actually are selected catchments. From this point, oops, it's actually picked up one there that shouldn't be a catchment. I must have turned one off. I want to do that again. I did too. I must have missed 2 lines up, but that's okay. I'll play on for today's purposes. I'm going to save a view, and I'm going to call this Runoff Nodes, and I'll use this as not only a selection but also a filter, because if I refresh XP tables by just closing and opening it, instead of all objects in model, I actually now have Runoff Nodes as a selection, and I don't have any of the extra nodes in my data set, which makes life easier to play with. So the next step that I want to do is take my area columns and my fraction impervious, and this could have a mix of 80%, 70%, 90%, 10% fractions impervious. Take it to Excel, and I'm going to hit paste. You'll note that the percentage here is not a decimalized percentage, so I'm just going to divide that by 100 and then run an equation that splits out my total area from my pervious and impervious components. So I'll give these some headers. So this is the impervious component, and this is the pervious component. And I've now split out my areas. I'm going to grab the pervious column first. I always like dealing with the pervious areas first. And back to the table, and I'm actually going to overwrite my area for subcatchment 1. I'm then going to go to subcatchment 2, and I'll bring in my impervious areas. I apologise, this probably feels mundane, but it just shows that it can be done very rapidly inside the software. I'm then going to grab the infiltration reference which we created before, which was the I = 0, C = 0 from my 100% impervious column areas. I'll sort by that area function again. I'm going to activate my second subcatchment. There are the little flags inside the software. And if I go back to subcatchment 1, I will make the impervious value here 0. So I now have 0 and 100 as my options. Turn this one off and copy these ones down just to clear those out. And I'll copy this one that we manually did before up and down the column as well. We have these tabs, and these tabs came with our template file that I started with originally. And so if I go to rain and infiltration, I can now change my routing method to Lawrenson, which is that one we did manually before. And I'll just copy that over the SCS methods. If you're in New Zealand, then SCS is probably going to be your friend. Likewise, Malaysia and India. We've got people from all around the world listening in to today's session. So you can pick any of the methods that you feel appropriate. The template file does come with the SCS methods, and for the Australians, then I'm going to grab the Australian rainfall runoff methods. But I'm just going to grab a 100-year 60-minute storm to start with. And now I really have fundamentally finished my hydrology, with the exception of telling the model how long I want it to run for. And to do that, I'm going to go to my job control. Job control is probably the most important part of anyone's model, and one of the probably least thought about. If you send a model in to us on support, this is the first place I go to check for errors in your file. So I'm going to run this model for 2 hours and hit OK, hit save, and all things being equal, if I hit solve now, it should solve. Oh, beg your pardon, I forgot to set the second subcatchment rainfall. So the software has given me that warning, that last little check that I missed. It's now helped me add an XP tables. I can just copy it down and I'm away. One warning there about it's only running the hydrology, not the hydrology and hydraulics. We'll fix that in a moment when I get to the hydraulics to quickly demonstrate that. I'll look at any one of these nodes and hit review results, and there is my discharge hydrograph. So that's useful. Now, one thing that it's very important for an urban modeler is to understand volumes. So not necessarily peak discharge. And to do that, we often look at a range of storms. So to do that, I can go to my runoff job control into global storms. And just for today, I'm going to run 3 storms, all large storms. I'll pick the 100-year 15-minute and the 100-year 25 and the 100-year 60 as my 3 storms. Just going to copy those names over to the name column, hit OK and OK. And now instead of just 1 storm, the software is quickly going to run 3 scenarios effectively, and we can try and pick which is the critical storm at this location. And in this particular location, it appears to me that the 100-year 25-minute storm is actually the worst storm, not necessarily the 100-year 60-minute on pure discharge. But if you have a look at the volume, clearly the volume of the 60-minute is much worse. So if you've had a detention basin in this particular project, first glance, my guess is going to be that the 100-year 60-minute out of these 3 storms will be much worse than the shorter duration storms. Just that volumetric change. And this simple graph here is one of the core reasons why the rational method really starts to hamper detention basin calculations. It just doesn't give us information about volume that we get by assessing either statistical patterns or real storm data. So I could theoretically go back and change back to the 100-year-25 if I felt I needed to model for pure peak discharge. But just for today's sample, I'm going to turn off global storms and continue running that 60-minute storm. So over to the hydraulics. I'm going to flick modes, and the good thing is randomly selecting this link here. 12D has been able to provide me with some information on elevations. It's a circular pipe, and we have information on the conduit profile for elevations. We're actually down near the ocean. Elevations below zero in this particular model. 750mm diameter pipe, ground elevations accordingly. Another nice thing that 12D does is it actually supplies us information about the design surface and potentially the natural surface if those layers have been allocated inside 12D. And so on this particular link, here is the details, and if I graph that, I get to see a variation in terrain, and that could be reflecting curb profiles or changes of terrain along this pipe, and that can actually plot out on longitudinal plans. So that's a very, very useful details, and one of the promised outputs from this is long sections with HGL, so we've got to get there as quick as we can. Another one that we've had a lot of questions on in the lead up to this webinar is to do with pipe losses or pit losses. And so pit losses inside our software are actually not directly allocated to the pit itself. And the main reason for that is because we can have very complex arrangements from any individual node or the representation of a pit per se. And so those losses are applied to the links that depart or enter into the pit, not explicitly on the pit itself. And so if we go to Conduit Factors, pit losses from 12D could come through here or can be manually applied with KU values of as high as 4 or other values, and you can manually define these. The issue for us in the short term is that they are fixed. So for the duration of your assessment inside our software, pit losses should be taken conservatively as the peak value for the entire duration, where pit losses in pure mathematics are actually variable. So that's a process that we're looking to improve inside our software to give users the flexibility of a dynamic pit loss arrangement, where at low flows the loss may or may not be as high as it would be under higher turbulent flow situations. A really good reference document for people is of course the Missouri charts. You can also go to the appendix of the Queensland Urban Drainage Manual, and also a reference document by the good John Argue from South Australia, and roughly the name of that document is the Stormwater Drainage for Small Australian Urban Catchments. Another really good reference text. In which case you might go to energy loss coefficients, where some people often run combinations of 0.5 and 1. But I wouldn't run an exit loss in this location here because it's not actually an exit. The exit from this system, if this was a head wall here, would be there. So we would only have a 1 applied at this location. I could talk a lot about entrance and exit losses, and if people do have questions, by all means hit us up after the session, and I'm happy to provide some further information or again some links to those references. We can also model blockage of systems in this particular dialogue. Blockage is an important part of urban drainage. It's potentially needs to be assessed, particularly in where you're reviewing an existing system, where blockage could be the reason for a failure. And so sediment depth does block from the bottom of the asset, whether it's a circular structure, a rectangular box culvert, or a channel. The sediment depth goes from the bottom up and is a very useful mechanism to model blockage. However, blockage can be modeled a few ways in our software, not just with sediment depth, because unfortunately the sediment depth is applied to the entire length of the structure. So in this instance, the blockage starts at this node and finishes at the downstream node. So therefore the hydraulics of the entire link have been affected by this sediment depth. And again, that may or may not be representative of your real-world case. So be cautious of that. And if we were trying to test some of the input that a tool like 12D or Civils 3D may have been able to give us with some indicative pipe sizes, XP Swim does have design functions, and we can design for freeboard to the surface with minimum cover content. We could also size for full flow and put upper limits on how many barrels you wish to have if cover becomes a constraint. The software will actually put in multiple barrels to help get you the discharge requirements from your project. I'm going to hit OK there. The next thing that I want to show, just quickly, some people who aren't interested in doing 2D drainage will often like to do what we refer to as dual drainage for overland flow in a road network. To do that, I'm just going to turn on my design surface, and I'll zoom in on this link, and I'm going to convert it to what we refer to as a multilink. Now on this multilink, I can take or apply a second entity to represent the overland flow, and in fact I'm going to do that as a natural channel and hit OK and call this R1 as an example. I won't do this for the entire network, but I'll just do it as a quick example. And if I right click on this, now that I have a natural channel, I can define a section layout. And so just going from left to right into about the crown of the road, I've extracted in a profile that I'm going to apply to this link. And now between this manhole or junction and this manhole, I have both the pipe and the natural channel. I would simply need to nominate that this ground elevation from 12D is now the invert of the structure, and I would need to ensure that I lift this particular elevation higher up into the air so we can actually fit the geometry of the cross section itself. So I might put in a value of 4 or some arbitrary number that's up in the air. And I'd also change the diameter to 0, which allows the software to interpolate the cross section itself. Also need to grab the length, which is not explicitly calculated automatically, but it's about 65.6 meters. We could also take that from the interface itself, and I can solve for slope. And off we go. And I've now fundamentally got a dual drainage network in that location. Doing that one at a time is a bit cumbersome. So to rectify that, we actually built in a utility that some of you may not be aware of, which is called our dual drainage batch converter. The dual drainage batch converter sits under our tools menu, and it's third from the bottom. And under this particular option, I can it asks for a shape, and that's the cross section of the road. And since I've got that one from the previous link, I'll use that as an example, but you could use template sections for local streets, access streets, highways, etc. Have them predefined, nominate a maximum depth we expect the depth of flow. So I'm going to put in 0.3 of a meter, and I hit convert. And it says that it's processed this one link. It's now become a multi-link, and all of the elevations for me, it's given a default name, but all of those elevations we played with before have been adjusted automatically, and it just lifted that previous ground level by that 0.3 of a meter that I'd nominated before. So in this way, I could change virtually the whole network in only a couple of clicks and convert it from just a pipe model to a pipe and overland flow model using that dual drainage batch converter. So a very, very useful tool in that simple context. If I were to hit run, again, the hydrology would come across and would be routed through these entities. But just quickly, I'm going to convert this model to a 2D model. There's another part that I wanted to do really, really quickly. And yes, for the moment. And to do that, I'm going to build in a very, very quick 2D model. And to do that, I'm going to apply some grid extents over my terrain. Very arbitrary, just to show you how quick this can be done. I'm going to set a 3 meter grid just for today's example, because I don't want too many cells. We can see that becomes quite dense and I've already got 16,000 cells. I definitely don't want too many more for that for a webinar. And I'm going to put a head boundary in over here, and I'm going to say that that head boundary is actually at set at a tidal value, and between 0 and 24 at mean high water springs, which in this location is about RL 0.4. Just a fixed boundary, and obviously there's lots of information on how boundaries occur. Each of those guidelines I spoke about before talks about boundaries, and definitely QDM goes into possibly the most detail. The last thing we need for a 2D model would actually be land use information, and as an example, I'll turn the I'm just going to change the contouring of this road to a 0.25, just so I can see that road a bit better. And I'm going to draw in a road. This information can be imported from AutoCAD or in a GIS file format. But just as an example, I'll just draw that small section. But I could theoretically draw the cul-de-sac. And to import from GIS, simply have to right-click that layer and import from a GIS. It does, however, need to be a closed polygon. So do be careful with how you draw these things outside the software. I'll leave that one basically as it is for the moment. All of the water in this project I already know is within the roadways for the way the model is set up. So I'm going to assume that for the rest of the site that it is actually already a road. And to play with that, I just need to set some further job control options for hydraulics. Run this again I'll only run this for 1 hour. Time control, I'm going to run this for 5 seconds for the hydraulics. I'll set an initial water level at 0.4 of a metre. Again, tying in so that the pipes start full at 0.4. We don't have a surge through the network. It's very important if you do have tailwater conditions that you try and avoid those surge components. And then I need to turn on my 2D. I have a 3 metre grid, so 1.5 second time step. If you did listen to our previous webinars on 2D modelling, you'd remember that. And map output, I've just got velocity and depth on for this example. Just want to try and be efficient about it. Last place that I can set an initial water level for the 2D is here. And I'll tick on folder options and I'm away. I've now fundamentally finished my 2D model with the exception of telling the 1D entities, i.e. the nodes, that they're to surcharge to the terrain. And to do that, I can use my Runoff Nodes filter in XP tables to adjust a core parameter here, which tells them to link the spill crest to the 2D. And I'll turn on the 2D inflow. I need to talk a little bit more about 2D inflow, but I think we've done that in previous webinars before as well. And if you're after more information on 2D inflow, again, we'll talk about that in Q&A or later. But I'm nearly done for this session. Should bring that down to about 2.6 again, since I played with that before. And what I can do, I can go into XP tables and go to my node table. Over here, junction data. I can change my connection to be on my ponding type to be link spill crested 2D. And I can copy this across all of the nodes again in this filter. That's the importance of that filter. And if I hit close, the last thing I need to do is turn on my 2D inflow capture, which I can use this copy parameter button, which is another nice feature in the software, and apply that across the network using my view. So I can restore the view here and hit paste across my network. Again, like before, all things being equal, I feel I've gone through all of my steps to get this model to run, but I need to tell it to run both the runoff and the hydraulics at the same time. So let's see if I've made a mistake. I've got a warning here saying that I've got some of my pipes less than 10. It's only a warning these days. It used to be an error. but I can press on with that for today's demo. All I need to do is type in a configuration parameter just to get rid of that warning, but the software will run as you can see that it is doing right now. Okay, I can now expand out my reporting layer, and I can see here that I have results for water depths, which I could hit play on. Speed that up just for the demonstration. And we can see water starting to pond up in some bioretention basins and throughout the network. So from go to woe, apologise, I probably spent a few more minutes than I would have liked, but I was describing the process as I was going. But I've got a blank model into a combined 1D, 2D model in just over half an hour. So that's not too bad, and all under the pressure of doing it live. So that's only part of it though. If we did go to the max water depths, again this is an indication I need a boundary over here, which I've only got the boundary on the northwest side of this model, but we'll ignore that for today's purposes. I could export that, hit print. So under our file print option, we could print that to plan at scale as well. So that's another nice function we have in our software. But really important is how these pipes perform and getting longitudinal sections. So if I right click on this node and select downstream objects, I can do a dynamic long section view. And we can see here I've played around, was the one I played around with the levels through here. And at this location we've also, this is another point, by reviewing the output I can see really this model's got a problem. The 12D input either had a typo or the designer hadn't finished his job before it was passed over to us. And we would most likely want to consider reviewing that inside SWIM or doing a pass back to 12D or your other civil package. The magenta line here shows the impact of the hydraulic grade line, and at times the relationship with the 2D. So where we see this marker in a 2D model means that water has been passed across to the 2D model. So that is a safety. If you've got a 1D model with the dual drainage functions and you see these waves, I will say that is a huge warning. You'd want to review your model because you could be losing water from your network and affecting your calculations quite seriously. Can be quite an important loss. My typical joke, and I'm not very funny, so my typical joke is that this point goes to the moon. It's completely removed from the calculations and never seen again. But we don't like to present that kind of a long section or even clever cross-section views on plan. We want to put things to CAD formats. So under our results menu, we can go to our profile plot. It's also F8 if you have a selection like so. So under profile plot, I'm going to set it to decreasing. So decreasing is for stormwater, increasing is for sewer. I'm going to call this line 8, which is what I think it is. Under our setup option, we can change what parameters we put on our output. So we can put freeboard, depths to invert, and you can customize this for your own company standards. But I'm just going to go with our default setup for today's example. Hit OK. I'll take scale to fit off and type in 1:10, but effectively this on these combinations is we've got to consider the paper size. I think this is an A3 piece of paper, not an A1 piece of paper. Hit OK, and I now have my long section, and if I just do a little zoom in here, that is the kind of output we can expect to see from XP Solutions products, particularly XP Storm and XP Swim, without too much duress. And if I hit the DXF button top left, that will actually push that out as a CAD file. And we're in the process of updating this particular function so that we can export the entire network in one go. And that should hopefully be finished for our next more important release, which is the XP Swim 2016.2, and that's probably going to be due later in the first half of this year, but sort of maybe March or April. But anyway, hopefully, as a quick, very, very quick overview of what you can do inside our software, going from external tools, building data into the model, as automatically as we can, playing around with some hydrology, getting into the hydraulics, linking up a simple 2D model and getting output. Hopefully that was a good overview, and you might have picked something up there to do in your own work moving forward. Otherwise, that pretty well brings me to the end of my demo. Just about to crack an hour. It's a bit longer than I was hoping for. I apologise, but hopefully you've enjoyed it. And I'll just duck back into my presentation. And just a last note before I get into Q&A. I've got some upcoming training over the next few months. Again, trying to wrap in some more of the content from Australian rainfall and runoff in Perth next week. So I'm heading over there for the weekend. Sydney in the early part of March and Brisbane in the early part of April. There's also training in Malaysia, I believe, on the end of February, and I believe there's also going to be a session in the Philippines. So training by the company in different parts at all times. So if you are interested in learning more about the software, or get in touch with us either via the phone on +617 331 02302 or ausales@xbsolutions.com.